have you ever stopped to think about how you can lift something that's, way too heavy with just a little bit of push? Or how something like tweezers can give you such perfect, precise control? Well, the answer is a simple machine that is literally all around us, and it's even inside of us. Today, we're going to unlock the secrets of levers.
So let's just start with a little bit of a puzzle. What on earth could a hammer, a tool for pure brute force, possibly have in common with a pair of tweezers, which are made for the most delicate, careful work? I mean, they seem like total opposites, right? But they share a really powerful secret.
Okay, so look at this. On one hand, you've got the hammer, letting you apply this massive force to yank out a stubborn nail. And on the other, the tweezers, giving you incredible precision. One is all about power, and the other is all about control. So what is the hidden link here?
The answer is surprisingly simple. They are both levers. Yep, it's a fundamental principle of physics that connects these two completely different tools. They're both designed to make a job easier, but as we're about to see, easier can mean a lot of different things.
So how can a hammer and a pair of tweezers be the same thing at their core? Well, let's crack the lever code. Turns out, it all boils down to just 3 simple parts that every single lever has.
This image right here, this perfectly captures the whole idea. You've got a simple rod, a pivot point, and a heavy object. These are the 3 key ingredients. You have the force you're putting in, the point the rod is resting on, and the big, heavy thing you're trying to move.
Okay, let's get these terms straight. The effort, that's the force you apply. The fulcrum, that's the pivot point. And the load is the thing you're trying to move. Effort, fulcrum, load. Remember those 3? They are the building blocks for everything we're about to talk about. So how do these 3 parts actually work together? Well, the seesaw is the perfect example. You've seen this a million times, right? How can a small kid balance out a much bigger adult? It's not magic, it's pure physics. It's all about where they sit compared to that pivot in the middle. This playground toy follows a very, very precise rulebook.
And here is that rulebook boiled down to a super simple formula. This is the law of levers. Basically, the effort you put in, multiplied by its distance from the pivot, has to equal the load multiplied by its distance from the pivot. It's the simple mathematical secret to getting everything in balance.
Now here's where it gets really fascinating. Just by changing the order of those 3 parts, the effort, the fulcrum, and the load, you create 3 totally distinct classes of levers, and each one has its own special superpower. And here's the cheat sheet. It's all about what's in the middle. For a first-class lever, the fulcrum is in the middle. For a second-class lever, the load is in the middle. And you guessed it, for a third-class lever, the effort is in the middle. Let's look at some real-world examples. First-class levers are probably the ones you think of first. The seesaw is the classic example, right? Fulcrum in the middle. But a pair of scissors works the exact same way. The little screw in the middle is the fulcrum, sitting right between the effort from your hand and the load, which is the paper you're cutting. Next up, second-class levers. This is where the load sits in the middle. A wheelbarrow is a perfect example. The wheel is the fulcrum, you apply the effort at the handles, and all that heavy stuff, the load, is sitting right in between. A bottle opener? Same exact principle. And finally, we've got our third-class levers, like a broom or, hey, the tweezers from our original question. With these, the effort is applied in the middle between the fulcrum and the load. And this kind of weird setup raises a very interesting question. So why have these 3 different designs? What's the point? Let's talk about the payoff for using a lever and how we can actually measure how powerful it really is. Which brings us to a really important question. We call these things simple machines, and we kind of just assume they always make work easier. But is that really true? Do all levers actually multiply our strength? To answer that, we need a way to measure how much a lever is helping us, and that's called mechanical advantage. Think of it like a power rating. It's just a simple number that tells you exactly how much your force is being multiplied. The bigger the number, the bigger the boost you're getting. So if the mechanical advantage is greater than 1, it means you're saving effort. You're getting more force out than you're putting in. But if it's less than 1, you're actually having to apply more force than the load itself. Now that might sound totally counterintuitive, but sometimes that's exactly what you want. Okay, so here are the golden rules, the key takeaway. Second-class levers, like our wheelbarrow, are always force multipliers. They always save you effort. Third-class levers, on the other hand, never save you effort.
And our first-class levers? Well, they're the wild card. They can go either way, depending on the setup.
So why on earth would we ever use a machine that makes us work harder? Well, it's because the payoff isn't always about force. Sometimes you're trading that force for something else, like safety or precision or even speed. Think about barbecue tongs. You want control and to keep your hands away from the heat. Or a fishing rod. A tiny flick of your wrist sends that lure flying. You've traded force for a massive range of motion and speed.
And now for what I think is the most mind-blowing part of this whole story. We've seen levers in our tool sheds and kitchens, but the most complex, the most important levers you use are the ones you're using every single moment of every day. That's right. Your own body is an incredibly intricate system of levers. The very same principles we've been talking about are what allow you to walk, to run, to lift, even just to hold your head up straight. In this amazing biological machine, your bones are the levers, your joints are the fulcrums, and your muscles, they provide the effort. It's just an incredible piece of natural engineering. And we can find all three classes right here in our bodies. The way your head balances on your neck, that's a first-class lever. When you go up on your tiptoes, your foot becomes a second-class lever, lifting your entire body. And when you do a bicep curl, your arm acts as a third-class lever. And now you know why. Our bodies are built not just for strength, but for speed and a huge range of motion. So you see, levers aren't just some dusty old concept from a physics textbook. They are a fundamental design principle of the world around us and inside us, from a bottle opener to your own biceps. So now that you're in on the secret, now that you see the pattern, what hidden levers are you going to discover today?